Welcome back. In this session, we will learn how to realize a discrete time system. Let's start. In the previous session, we learned the general nth order differentiation that describes a system. All right, so we learned the general nth order difference equation. We saw this in the previous session. L is equal to B naught x of n, B1 x of n minus 1, plus so on, Vm x of n minus m. So this is an nth order difference equation which describes a discrete time system, and we learned the nomenclature in the previous class. And what are these A1, A2, An, B0, B1, so on up to Bm? These are the coefficients of this difference equation. So these are the coefficients of this difference equation. So on up to Bm, right? Now we know this is a difference equation that gives us the time domain behavior of the system. We know a discrete LTI system is characterized by the impulse response, and in the frequency domain, it's characterized by the transfer function. It's characterized by the transfer function. So this is the impulse response of the system. And this is the transfer function of that system in Z transfer function, in Z domain transfer function. Now, how do you obtain this transfer function of the system? And how do you obtain the impulse response? Now, impulse response means when the input to the system is delta n. So substitute in place of x of n, put this equal to h of n, you will get, sorry, delta n, you will get h of n, and is the impulse response of the system. We'll not do here, we'll do the only the transfer function of this. Now taking Z transform of this expression, so taking Z transform of this expression on both sides, and let's suppose Z transform of y of n is y of z. Now Z transform of this term will be, this is a constant, A1 is a constant, so the Z transform of this will be A1 Z inverse y of z. So y of z. If Z transform of y of n is y of z, then Z transform of this term will be Z inverse y of z. Same way, the Z transform of this term will be A2 Z base power minus 2 y of z. Same way. So we can write it like this: A2 Z base power minus 2 y of z plus so on plus AM Z in base power minus n y of z is equal to B naught x of z means Z transform of this term. Then B1, this is the shifting property. Actually, I'm following the shifting property of Z transform. Please have a look at that. X of z plus B2 Z raised power minus 2 x of z plus so on Bm z raised power minus m x of z. Right? So taking y of z common, we say this is 1 plus a1 z inverse plus a2 z minus 2 plus so on am z is 1 minus m is equal to b naught plus b1 plus b2 plus so on bm z is 1 minus m x of z, and we can write it like this: yz divided by x is dividing both sides by x of z, and taking this term on the right hand side, so this will be b naught plus b1, z inverse 1 plus b2, z inverse minus 2, so on up to bm z raised by minus m divided by 1 plus a1 z inverse plus a2 z raised by minus 2 plus b an, not bn, an z raised by minus a, right? And what do we say? Output by input transformed, output by transform input, as transfer function of the system. So the transfer function of this system is, so this is the transfer function of this system. So this is the transfer function of this system. So the transfer function of this system is, we can also write it like this: h of z is summation k running from 0 to m bk z raised by minus k divided by 1 plus summation k running from 1 to k running from 1 to n ak z raised by minus k. So this is also the transfer function of the system. So we can also write it like this. So this is the transfer function of the system. Now have a look at this difference. This transformed equation are the general and authority difference equation. Have a look at this. What are the components that are required to realize this difference equation? What do you have? You have first of all y of n, that's the output of the system. Then you have a y of n minus 1. How do I obtain y of n minus 1 from y of n? Now this simply means delayed version of y of n. So the first component that you require is the delay component. So the delay component, this is also referred as memory. Means you require the memory, because to store the previous value of the output, you require the memory. So we say the first component that's required is the delay. So there is also delay here, delay here. Now depending upon how much delay is required, that will decide the memory of the system. That will decide the memory of the system. Then what we have, there's a coefficient and it's multiplied with the previous output. There is a coefficient and it's multiplied with the present input. So there are different coefficients and these are multiplied. So this is the first component. So the second component that's required here will be the multiplier. So this is the multiplier. So there are multipliers are required for this. And the third component that's required here is the adder. There are different addition operations here at these locations. So the third component that is required is the adder, or this is also referred as summer. In discrete time we also call it summer. All right. So this is, if you have a look at this discrete time system in time domain and the same discrete time system in frequency domain. This is the frequency domain relationship. Either this, or this. This is one and the same thing. So this is the frequency domain relationship. Same thing. This means a delay. Z inverse means simply a delay. In time domain, it means a delay. Or the memory component, you can call it. There is a coefficient that means you require a memory. Sorry, multiplier, and there is an adder operation or a summer operation that takes place. Right? All right. So what are the different components required to realize this difference equation? General and authority difference equation. Let me rewrite it here. A1 y of n minus a is equal to summation k running from 1 to m bk x of n minus k. So there is summer, there is multiplier, and there is the delay component. Alright, so the three components that are required are to realize this system are. Now how do we draw these systems? First I require a delay component, so the memory component. Now in discrete time we denote it like this. So this delay component is denoted by like this. So this is the delay component and we denote it by z inverse. In frequency domain, we denote it by Z inverse. This means the delay. Now, if we say x of n is the input, the output will be x of n minus 1. Right? So this is the delay component. And if we say x of z is the input in Z transform, then the output will be here Z inverse x of z. All right, so this remains the delay component. So in time domain, if I say input is x of n, output will be x of n minus 1. In frequency domain, we are in terms of Z transform. If I say input is x of z, output will be Z inverse x of z. Right? This is how we show the delay component. So this is the delay component. Same thing if the input is y of n. So if the input is y of n, like this, and we denote it like this, Z inverse is the delay component. If the input is y of n, the output will be y of n minus 1. Or in frequency domain, if the input is y of z, output will be z inverse y of z. So these are delay components. So the first component is the delay component, or you can also call it memory. This is also memory. This is also referred as memory component, right? And the next component that is required is the multiplier. Now, how do we denote the multiplier? How do we write the multiplier component? Multiplier is denoted by like this. This is the multiplier component. This is how we show a multiplier. Now, if I say input is x of n minus 1, suppose the output, if the multiplier is y a1, then the output, let me use b because we have used b coefficients with input. So let's suppose input is b1, so the output will be b1 x of n minus 1. All right, so same way, if the input is z inverse x of z, output will be in the frequency domain b1 z inverse x of z. So this is in terms of input. Now in terms of output, I can draw the same component, and I can draw it like this. If the input is this, output is this. So if the input is y of, let's suppose, n minus 2 this time, and this has a coefficient multiplier is a2, so you can write it a2 y of n minus 2. This is showing one component only. Okay, this does not delay any the input, it only multiplies the input, means it scales the magnitude or the amplitude of this sequence. Now you can say if the multiplier coefficient is a2, it simply multiplies with this input, that's all. But this operation in the frequency domain, so the input will be y of 2yz, right? So the output will be a2 z minus 2 y of z. I hope you understand this. And this simply means this is a multiplier component. I'm showing just one example here, right? I'm taking this as the example of input, and this will be the output. All right, and this is the multiplier coefficient. Please remember, this is just an example. Now, how many multipliers are required here? How many multipliers are required here? If you look at this, there is one multiplier, two, so on up to n multipliers for the output, and 1, 2, so on up to m plus 1 multiplier. So m plus 1 plus n multiplier. This is the total number of multipliers that is required here. So the total number of multipliers that will be required is n plus m plus 1. This is the total number of multipliers that will be required to realize this nth order difference equation. All right. Same way, how many delay components will be in general used here? You can see there is one delay, two, so on up to nth delay. Then we have mth delay. So n plus mth delay components. So how many delay elements will be used here? Other memory elements will be used here. N plus m delay components, right? So you can say these are flip-flops simply. This from digital point of view, you say these are n plus m flip-flops. or resistors, whatever you call it. Now the third component that is used here is the summer. Third component that's used here is a summer. And how do we denote a summer? We say summer is denoted by this, and we use this symbol. This is a summer, and let's suppose the input to this is this and this, and suppose the in time domain if the input is x of m and y of m, the output will be x of m plus y of. In the frequency domain, if we say in frequency domain, you can say the input will be x of z or y of z. The output in the frequency domain will be x of z plus y of z. Right? This is how we show the outputs in frequency domain. Alright, now let me give you one more example. Let's try it again. So if the summer we show by this symbol. So if the input is suppose x of m, and let me suppose a1 y of n minus 1 in time domain. So the output will be, this is just an example, output will be this plus this. So output will be x of m plus a1 y of n minus 1. This is just an example. And in frequency domain, I can write the same thing like this, x of z, a1 z inverse y of z, because I know that z transform of this is this. Z transform of this is this. So we can write the same output in frequency domain as x of z plus a1 z inverse y of z. So this is the output in time domain. This is the same output in frequency domain. Now how many adders or the summers are used here? So how many summers are? So how many summers are used here? Adder, you can call it. An addition operation in short. How many adders or summers are used here? If we go back to the differentiation, this. How many adders are used here? 1, 2, so on up to it will be n minus 1 actually. Then there are m summers here, I think, and I m summers. So we can say please check it. So the number of summers will be n minus 1 plus m summers. So this is the total number of summers that will be required to realize this anatomic difference equation. Alright. So this is the total number of elements that will be used here. Alright. So how do we do this? How do we realize this? Let me give you a quick overview. How do we realize this? Let me redraw the difference equation. Let me rewrite the difference equation. What do we have? Output is equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus so on up to bm x of n minus m minus, I'm transferring the previous outputs on this side, a2 y of n minus 2, a3 y of n minus 3, minus so on up to an y of n minus, right? So this is our differentiation that we want to realize. Now have a look at this. How many multipliers are here? How many multipliers are here? M plus 1 multipliers. How many multipliers are here? N multipliers. So this is